So what is going on with all of the clotting post-COVID? What can we learn about that from science? I've been studying this topic for many months, and now there's a lot of new emerging information as to what might be causing this, what's forming this, who's getting it, why are we even seeing this, why is this happening? And this is going to be a new series dedicated to this topic, and it will have many videos because there's a lot of science behind it and it's very complicated, and I do want to be very thorough because this is probably some of the most important information, and it's all related to the very common problem we're experiencing post-infection, which is long COVID. In this video, I will review how does coagulation happen, or basically how do we form clots normally. This background information is integral to this series, so we do need to review this. I'm going to talk about long COVID as well, what it is, what clinically might be happening with this. Then we're going to move on in the future video installments. In the next video, we're going to talk about the clots themselves, these unusual clots there. It's what's also remarkable is that the clots themselves are not normal. They actually do not resemble the typical clots you would be expecting at all. So we're going to be looking at a lot of pictures as to what do they look like under a microscope and why they're abnormal, and how they're formed as well. And those are really fascinating images, so stay tuned for that. It's like looking into the sky, and depending on the size of the clots, you can either see fluorescent stars, or if they're big, we're going to see images that resemble more like supernovas. So stay tuned for that. In the follow-up video to that, we're going to talk about amyloidosis, which is basically when proteins are not folded properly, and as a consequence they can assemble, and many of such events are involved in many diseases. So we're going to talk about this because that's one of the big issues with these clots. They're not normal. They follow pattern of what we see with other amyloid diseases. A couple of examples of that is like what we see with, say, prion proteins in mad cow disease or Alzheimer's disease. So that we're going to talk about that. Then we're going to have not one but two videos dedicated to how the spike protein itself is involved in this. It's a big player. There's a lot of science now emerging on how spike protein might be contributing to this formation of these abnormal, bizarre clots. So we really need to break this down. Very, very important information. Then we're going to talk about how other components, what other components are involved in these clots. And then finally, we're going to wrap up this series with one video dedicated to how can you measure for whether the person is potentially afflicted by this phenomenon right now or not. And the last video will be dedicated to what can we do for potential treatment. So big series. Let's get started. My name is Dr. Mikola Rashek of Neurogenomics. And let's get going with the review of the coagulation pathway itself. So coagulation or formation of clots is an absolutely normal thing that is supposed to happen in order to preserve the proper function of our vasculature. So that means if you have a breakage, a hole, crack in your blood vessels, we need to be able to fix that. That's where clots are extremely valuable and important. And there's two pathways involved in the process, kept in a fine-tuned balance. One of them is called thrombotic pathway. So what's in the name? The name has the word thrombus in it, which is a fancy schmancy way of saying clot. So thrombotic pathway is a pathway that forms clots. And that is juxtaposed by fibrinolytic pathway. And what's in the name? First, let's see the word lytic. That basically describes the word lysis, which is also a fancy schmancy way of saying breaking things down on a molecular level. And then fibrin is the total star of the show. We're going to talk lots about this. Fibrin is the primary component in the formation of clots. So these two pathways are supposed to be regulated to exquisite level in order for the body to achieve two things. No hemorrhage, meaning no bleeding from your vasculature, and no thrombosis, meaning no clots forming where they're not supposed to be happening, so that we do not obscure proper access of oxygen to the tissues. All right, so, and like many things in biology, in our human biology, there's a fine-tuned process involved keeping things happening in a very narrow window of keeping everything properly balanced. And if you go outside that window of proper balance, this is how you can start forming diseases. All right, so let's start breaking these pathways down in detail. And let's start with the thrombotic pathway. So how do we form clots? So we're going to start with a protein called tissue factor. And it's an interesting little guy. It's embedded in membranes of cells, endothelial cells. So these are the cells that form the lining of the vessels, and they're hidden. So remember, membrane of the cell is the coating that surrounds the cell, and it's made out of fat. And many proteins are embedded in that. Tissue factor is one of them, and it's hidden until you have a breakage in that blood vessel wall, and the breakage will expose tissue factor. And now tissue factor can do its own magic, which will activate a specific factor, which itself then activates a certain cascade of events. It's like a chain reaction. And the final outcome of this chain reaction is to basically activate thrombin, okay? And then thrombin itself works on fibrinogen, the molecule of interest for us in this video, and it processes fibrinogen, and what it does, it cleaves a couple peptides off of fibrinogen. So what are peptides? Let's maybe define that. So remember, proteins are long chains of amino acids put together. Amino acids are the building blocks of proteins. So when you have mRNA, which is genetic blueprint telling our cell how to build the protein, which is basically some form of a little molecular robot inside our cell that will do some function. When you use that genetic blueprint, mRNA, the genetic information tells certain machinery which amino acids are supposed to be put together in contiguous or continuous array, and you basically glue a bunch of amino acids together. So you create a long chain of amino acids. This long chain of amino acids can then take form and take shape. And to create a certain three-dimensional shape. So that's a protein. Now, if you have only few amino acids together, that's a peptide. So that's basically what the definition of peptide is. So peptides is a short fragment composed of few amino acids. So thrombin basically cuts off few amino acids, two kinds, two peptides, and not only does that lead to a certain change in a fibrin, three-dimensional change, it also leads to change in the name. So it's no longer, the molecule is no longer, after being processed by thrombin, it's no longer called fibrinogen, it's now called fibrin. So that's the relation there. And fibrin has the ability to now form the clot. So let's talk about fibrin in a bit greater detail. And fibrin actually is one of the most common proteins circulating in our blood. It's basically, if you were to look at the numbers of it, let's see, we're talking about somewhere between 1.5 to 3 grams of it per liter of blood, or another way to put it is 1.5 to 3 milligrams per milliliter of blood. That's a lot. Now let's juxtapose that with something like spike protein post either infection or vaccination, and the typical measurements of the spike protein levels in the blood are about somewhere in the order of picograms per milliliter of blood. So what is that unit? So if you have a milligram, which is a unit of measure you should be familiar, and you divide that by 1,000, that's how you get to microgram. And if you take microgram and you divide that by 1,000, that's how you get a nanogram. And if you take 1 nanogram and you divide that by 1,000, that's how you get to the picograms. So you can probably appreciate that milligram quantities of protein in 1 milliliter of blood is a lot. It's a lot. Now at this stage, before it's being processed by thrombin, fibrinogen is referred to as soluble. It just happily floats around until it's called into action by thrombin. So then when those peptides are cleaved on fibrinogen to create fibrin, now fibrin has new abilities. So now what is fibrin made of? It's made out of 3 different long chains of amino acids that kind of wrap around each other, and they form a 3-dimensional shape that the authors who we studied the most for this series, which by the way, these are experts in clotting, and one of the teams, the primary team, comes from South African University. So just FYI. And I liked it because they called it resembles like a cigar, shaped like a cigar, okay? So at this point, think of the fibrin has it's like a long stick, but has nodules on it. So it has one big nodule in the middle. That's called appropriately central nodule. And then it has nodules at the very end. And these are called D regions. So then imagine if my head and my outstretched arms were fibrin, of course, 2 arms, I can only show you one, then imagine my head is like the central nodule, and I don't have elbows anymore, so my arms are stiff, and then my fists, they're like the end nodules, so they're like the D regions. When you clip those peptides, you clip them off of that central nodule. So imagine you clip something off of my head, and now my wrists can be used to grab my head. But I cannot grab my own head because I don't have elbows, so my arms are stiff. I can only grab head of adjacent fibrin molecule. So you can appreciate how suddenly you can quickly start stacking fibrin molecules one to another, and this is how rapidly you can create a little chain of fibrin molecules glued together or linking together, and basically you create like a wire. But there's something else happening. At my wrist, I also have this string hanging off, okay? And I can use this string to tie 2 wrists together. So I'm tying 2 D regions together. And when you link 2 D regions together, That's how you form D-dimer, a name we're going to talk about that in just a moment. So I can tie these wrists in some sort of a kinky molecular bondage, not only between two adjacent fibrin molecules, I can also do it between different wires of long fibrin molecules. So in this way, you can appreciate how you could rapidly create a clot. Now the molecule that does this linking, its actual chemical bond, it's called cross-linking. That molecule is called factor 13. And I'll mention it now only because we get to see it later on in our discussion in just a moment as well, if I remember to mention it. So that's basically how you can create the clot. Now, let's talk about how you break it up. And the central molecule here that does the magic is now called plasmin. And plasmin will cleave these clotted fibrins exactly where the wrists or those D regions are tied together to form the D-dimer. So that's what the plasmin will cut off. And this is how you release D-dimer into circulation. So when plasmin processes a clot, and that's how you end up with D-dimer in circulation, you can measure that. So what do D-dimers tell you? D-dimers tell you the history of how much clotting has happened. And it's one of the most common measures for potential associated risk with COVID-19 severity. But what D-dimer levels do not tell you about is one, how many clots you still have left in the body, and number two, whether they're normal clots or whether they're abnormal clots, because remember, the key here is that the clots we're forming in long COVID patients with the spike protein involved in, they're not normal. So D-dimers will not tell you that information at all. But let's go back to plasmin. How do you get plasmin? It comes from plasminogen, and plasminogen itself is processed by, I believe, molecule called tissue type plasminogen activator. And that molecule basically binds to fibrin. So what you have is the more fibrin is being used for clotting, then eventually you will also start assembling this molecule, which can cleave plasminogen to process it into plasmin, and plasmin will start cleaning up the clots. So remember, we went from fibrinogen to fibrin. Now we're going from plasminogen to plasmin. And this tissue plasminogen activator is so powerful that it is also used as a medicine. It's that powerful in being able to clean up clots, okay? So that's another extra tidbit of information for you right there in terms of clotting. But you can also inhibit function of plasmin. So there are molecules that will stop it from working properly. One of them is alpha-2 plasmin, alpha-2 antiplasmin. That's what that name is. And the reason why I mentioned that factor 13 molecule that is involved in tying two D regions of fibrins together. Remember when I can tie my wrists of one fibrin molecule adjacent to another wrist of another fibrin molecule, and we can tie those together. That same molecule can also link molecularly or chemically that inhibitor of plasmin onto the clots as well. So I thought that was interesting. This is how you can fine-tune, regulate how much clot you're producing and how easily it can be also removed. Now, another inhibitor of plasmin is plasminogen activator inhibitor 1. So it's like a double negative in the name. And we're about to be hearing about that in just a moment as well. So those are the pathways. This is how you're processing clotting. Okay, now we're going to jump into basically long COVID, also referred to as post-acute sequelae of COVID-19. Now, the word sequelae is just a fancy schmancy way of saying complications. So post-acute complications of COVID-19, if you will. But you can see why long COVID stuck as a better name. It's shorter. So long COVID, unfortunately, it turns out, has the possibility of being extremely common. Very unfortunate, because it is estimated that even potentially up to 1/3 of all people infected with COVID might end up suffering from long COVID. So this is not a trivial thing. We're learning that this could be a potentially problematic disease affecting many people. It has many different symptoms. And speaking of fancy schmancy words, one way to describe that is that the disease has multifarious symptoms, but the most common symptoms we encounter are breathlessness, fatigue, chest pain, brain fog, it's a common one, right? Inflammation, tissue damage, and the one we are focusing today, topic du jour, is of course formation of microclots or clots, depending on their size, I suppose. And more specifically, what the authors refer to as coagulopathy, or the dysregulation of proper blood clotting, because what's so unusual about this dysregulation of proper clotting is that you can both have hemorrhage or excessive bleeding and clotting in the same individual. And we're going to talk about that potentially why. Remember, these were the experts on clotting that are producing a lot of this research. And so they propose certain molecular pathway mechanisms of how this might be formed. But just before we get there, what is believed that is causing long COVID? What are the contributing factors? Okay, so one of them is viral persistence, meaning virus is sticking around in a person for a long time. And we're going to make other future video on this topic on how this might be achieved. Another one is obviously these clots, and associated with the clot formation is unusual hyperactivation of platelets. Platelets also play a very big key role in clot formation. So having hyperactivation of platelets is also not good. It can lead to problems as well. Another one is autoantibodies. We'll talk about that in a moment. Basically, what we're talking about is formation of antibodies that can instead attack you yourself, instead of them attacking something you don't want in the body. So obviously, unwelcome thing. Proper function of the immune system is dysregulated as well. There's excessive tissue damage as well. And we're going to talk about that, why that might have been happening. And the final one that they also mentioned is reactivation of dormant viruses, which is, remember what happened to Justin Bieber. So numerous of these factors could be working together in producing long COVID in any given individual. There's one more that these authors didn't specifically mention that I think is important to state, and that is dysregulation of your gut microbiome. And we're going to talk about that in a future video as well. Basically, all the bugs in your gut, their composition is messed up because of the infection, and that can also have its own influence as well. All right, so this is basically what's happening with long COVID, which at first was a bit of a mysterious and wasn't even certain if it's real. So here we are now observing it in a lot of people, and there's rapidly information is coming out on this. So let's talk about how can we get both bleeding and clotting in an individual. And this is the part that I really enjoyed that the authors proposed. And basically, remember, when you have virus infection, the virus spike protein interacts with ACE2 receptor on the surface of our cells. Now, ACE2 stands for angiotensin 2 converting enzyme. So basically, it's an enzyme that works on this molecule called angiotensin 2. And this is how we regulate blood pressure. So this receptor for the virus has an important own biological function. So, but one of the ways how virus can be taken up is that the virus bound to the receptor in that interaction can be literally swallowed up by the cell. So it's taken up with the receptor inside the cell. So what does that mean? Basically, you're removing certain amount of that ACE2 receptor from being able to perform its proper function. As a consequence of that, it's kind of windy here. I wish I could show you the view. As a consequence of that, you have buildup of that angiotensin 2 molecule inside the blood. And of course, not only are you start messing up the blood pressure because of that, but also this buildup, the authors claim, eventually will lead to the activation of that inhibitor of plasmin called plasminogen activator inhibitor 1, the one with that double negative there. And that, because it inactivates plasmin no longer now is available for proper breaking down of clots, and voila, the fibrinolytic pathway is shut off and it's no longer properly working. So this is how they explain. Of course, if you have a buildup of clots, then that will lead to cytokine storm and inflammation. That in itself will promote further clotting formation. And on top of that, remember, spike protein, we'll be discussing this in future videos, might also be involved in promotion of creating of these clots as well. So you not only might have a trigger to create clots, but on top of that, you might have a trigger to prevent its proper removal. So that's on top of that. Remember, I mentioned that platelets are also activated. Activated platelets themselves can lead to buildup of other family members of angiotensin molecules in the blood, which also will lead to further activation and buildup of that plasminogen activator inhibitor 1, which is an inhibitor of plasmin. And here you go, you have a shutdown of that fibrinolytic pathway. So this is how, as a consequence of this shutdown though, you also now have a buildup of tissue type plasmin activator, and as a consequence, you also have the possibility of overactivating plasmin in other areas. And this is how the authors say this dysregulation could be leading to both changes from being able to have hemorrhage and also excessive clotting. So very interesting, somewhat unusual. I thought I would share this because this is still a bit of a molecular mystery, if you will, okay? Okay, so then before I move on, one very interesting aspect that is worth mentioning as well is that long COVID in its symptomology or its symptoms is very similar in presentation to already other well-known disease, or actually I should not say well-known. It was quite mysterious for a long time, but now it's being more appreciated and understood. And that is myalgic encephalomyelitis, I think is the name. If I messed that up, hey, it's also known as chronic fatigue syndrome. So, exposed to heavy wind. Bear with me for a second. Let's show you the background. Okay. And such a heavy wind, I have to hide again. And basically, they have very similar symptoms. Again, fatigue, excessive fatigue is common. Oh, by the way, myalgia is another symptom of long COVID as well, which is, again, a fancy schmancy way of saying muscle pain. So chronic fatigue syndrome has similar symptoms. It's known that you can have a normal, healthy person and that person can have a certain infection and they can develop this disease. And becoming easily fatigued after exercise is one of those common symptoms as well. So there is that similarity. What this means is that now, because we have so much long COVID to deal with, potentially, hopefully, eventually the treatment for long COVID might be helping people with that condition as well. So that's the hope, okay? Now, before I finish, a couple more things. One is, how is long COVID triggered clinically? What is happening? And the number one reason, there's three reasons. Number one is that we might have lack of proper oxygen being delivered to tissues. There's a couple reasons how this might be achieved. This is called hypoxia, not enough oxygen reaching tissues. Number one, obviously we're creating clots. These clots can be, if they're very numerous, they will start blocking the smallest of the blood vessels. These are called capillaries, and you will actually not have enough blood cells flowing into tissues delivering oxygen. And the authors believe that this lack of oxygen delivery is probably the primary reason that actually explains the vast majority of all of the symptoms observed with long COVID. And there's another problem. Remember, virus infection, SARS-CoV-2 virus infection can also disrupt proper function of mitochondria. So even if you do have access of oxygen to the cells, you can also have inability of these cells to properly process that oxygen to produce energy, because mitochondria function might be disrupted. So that's number one reason. Number two reasons are the formation of those autoantibodies. So what are we talking about here? So why do these antibodies form? They form when you have presentation of molecules that are misfolded, and therefore they're not presented normally. And as a consequence, the body now sees molecules that are supposed to be normal to us as something foreign, and it will create antibodies against it. Now, autoantibodies are well understood that they actually can be linked to the severity of COVID-19, and it has been previously observed that the more autoantibodies a patient with severe COVID-19 had, the more likely they were to potentially die of COVID-19. And last thing is that vagal nerve could be disrupted. We're not going to talk about this. We'll talk about this in the future videos. The very last thing I want to mention is vaccinated individuals. Are they affected any different? And it looks like the vaccinated individuals are just as likely right now to suffer from long COVID as unvaccinated individuals. The likelihood of that is similar. That makes sense, because right now we know vaccines do not protect from infection. However, if there are two other things, if you look at symptoms, they have very similar symptoms. The only difference is that vaccinated individuals are less likely to suffer from myalgia, that muscle pain and fatigue, so that's good. And then finally, one of the papers mentioned that there is absolutely no evidence that vaccinal spike protein is contributing to these microclots, and that is true. But what these authors did not mention or add anything to that is that at the same time, no one has looked at it yet. So while there's no evidence, it's not because we prove that there is no evidence, it's simply there is no evidence because no one ever looked at it. And this is one of the common problems in how science was often described during the pandemic. So lack of evidence is not evidence in itself that something is not actually happening. But I thought I'd mention this as well. All right, so this wraps up this first long video. I'm gonna end it right there. Check out my Patreon account as well for other videos as well that are not listed on this channel. Please subscribe, please like, please share, and check out my COVID-19 Q&A event. Thank you everyone for your attention in this video. And let me show you, before I wrap it up, one last view. And bye everyone, ciao for now.